In this session, we are going to discuss correlation measures between two variables. Especially, we will introduce covariance and correlation coefficient. Before we introduce covariance between two variables, we will first examine or review the variance for a single variable. What is variance? I think you all know what is average. For example, the average salary of employees in a company. Okay. The average, also called mean mathematically, represented as mu. So mu actually is the expected value of x. However, if we just use mean, we may not be sufficiently represent the trend or the spread of the value in variable x. Okay. For example, we may not only like to know the average salary in a company, but we also like to know how these value spreads. That means whether they are very close to the middle, to the mean, or they are widespread, they have many very high salaries and many very low salaries. Okay. In that case, we introduce the concept of variance, which actually is to measure how much the value of x deviate from the mean or the expected value of x. Essentially, we use sigma square to represent the variance of x. Sigma is called standard deviation. Okay. Variance of x actually is the expected value of x deviate from the mean. If we take the square, simply says no matter it's positive or negative, we all change them into positive. Okay. Then if x is discrete variable, okay, then the formula is written like this. That simply says we use sum of this function. Okay. This function is actually x deviate from the mu, from the mean value, take the square times x density function. Okay. If x is a continuous variable, so we will take integral where the range is from minus infinity to infinity. To that extent, we say variance is the expected value of the square deviation from the mean. For this formula, we can also do a little transformation. For example, we can transform for the expected value of x, square deviation from the mean, we can write down its expected value of x squared minus mean square. Okay. This transformation actually has been introduced in many textbooks. It's quite simple. We're not going to introduce here. In many cases, if we write in this form, it may lead to more efficient computation, especially when you want to do incremental computation. If we take a sample, then the sample variance is actually the average square deviation of the data value xi from the sample mean mu hat. So the sample variance is written as sigma hat square. So we often use this formula or use a similar transform formula to compute it. Now we introduce a covariance for two variables. Once we get two variables, x1 and x2, we want to see how these two variables, they change together, whether they are going up together, going down together, which could be the positive covariance. Okay. Let's look at the definition. The definition actually, original definition is x1 minus mu1's square. Now we see actually these two variables, we want to see x1, the difference from its mean value of x1. x2, the difference from x2's mean value or expected values. Then we look at their expectation. Okay. Mathematically, we also can transform this into this form. Okay. If we get a sample covariance, we look at the sample covariance between x1 and x2. So the sample covariance is calculated by their difference from the sample mean. Okay. So that's also popularly used. Okay. Actually, the sample covariance can be considered as a generalization of sample variance. For example, originally we want to look at the two variables x1 and x2, their covariance. But if we think these two, x1 and x2, we replace it by x1. That means we just look at the two variable x1, what is their covariance? Then we can represent this 2 by 1. Then in that case, the sample covariance formula, we look at this formula, we change the variable from I2 to I1 and mu2 to mu1's hat. So then we will derive this formula. This formula essentially is sigma 1's hat and its square. Okay. So we probably can easily see the sample variance is just a special case of sample covariance when the two variables are just the same. When the covariance value is greater than 0, we say it is a positive covariance. If its value is less than 0, it is negative covariance. Okay. If these two variables are independent, then their covariance is 0. However, the converse is not true. That means not when the covariance is 0 does not mean x1 and x2 are always independent. Only under certain additional assumptions. For example, if the data follows multivariable normal distributions, in that case, the covariance of 0 implies independence. Now we look at a concrete example. Suppose we have two stocks, x1 and x2. They have the following values in 1 week, like these 5 pairs of values. Okay. Then the question is, if the stock whether the stock, okay, affected by the same industry trends. That means whether their price will rise or fall together. Okay. Then we calculate their covariance. We will be able to know whether they are positively correlated or negative one. Okay. So if we look at the covariance formula, especially we use a more simplified computation formula, then we can calculate the expected value of x1, which is the mean value of x1, the expected value of x2, which is the mean value of x2. Then we look at their covariance. Actually is, we use this formula. We look at their product, their dot product, the sum of, then divide by sum of them, divided by the number of variable pairs. Then we minus, this is expected value of x1 and expected value of x2. Then we get the final value is 4. Okay. That means the covariance is greater than 0. That means x1 and x2, they rise or fall together. Then if we want to normalize them, we will introduce correlation coefficient. That means for two numerical variables, we want to study their correlation, which essentially is the standard covariance. That means we want to normalize the covariance value with the standard deviation of each variable. So it is defined as correlation coefficient is the covariance divided by the product of their standard deviation. Or you can say the covariance is divided by the product of variance get their square root. Okay. So if we look at sample correlation for two attributes x1 and x2, then essentially we get a row 1, 2's hat is equal to the sigma 1, 2's hat is essentially their sample covariance divided by their sample standard deviation. In a concrete formula, we can write in this way. Okay. Then if this correlation coefficient is greater than 0, that means A and B are positively correlated. That means x1's values increase as x2s. The higher value greater than 0, the stronger correlation. Okay. If rho 1, 2 equals 0, that implies they are independent under the same assumption as discussed in the covariance. If they are less than 0, they are negative correlated. Then we can look at a set of variables. We can see, for example, for two variables, when they are perfectly negative correlated, they line up like this. Their correlation coefficient is -1. Okay. Then if they gradually become not so perfectly negative correlated, you will see their trend. When this value is 0, you could not see anything like a positive correlated or negative correlated. But when you gradually grow these correlation coefficient, you will see their value become more and more correlated. When they are perfect correlated, then the correlation coefficient is 1. That simply says the correlation coefficient value range is from -1 to 1. Okay. Then if we draw this in the scatter plot, we'll see the set of points, their correlation coefficient changes from -1 to +1 in this shape. In many cases, we may want to write, for two variables, we may want to write their variance and the correlation information into the 2x2 covariance matrix form. Okay. For example, you may say the variable 1 is self-correlation. Essentially their variance is this one. And for their covariance between 1 and 2 is defined here, between 2 and 1 is defined here, and then that's variable 2's variance. So this is a typical, 2x2 covariance matrix. In general, if we have d numerical attributes, that means suppose we find a data set, it has n rows and d columns. That means we really have d numerical attributes. Then their covariance matrix essentially is written in this form. You probably can see this is the variance of variable 1. This is variable of the second dimension. This is variable of the d dimensions. Okay, and their covariance for each one will be lining up like this. And we give a few interesting additional reading. These are the several books. They contain interesting chapters discussing the different measures. Thank you.